Hello everyone, welcome to another video. Today we're going to be plotting a rational function, and so that's just going to be the main idea, is putting some rational function on a graph. And if you remember, a rational function is just one that can be written in the following form. So the rational function in terms of x is just some numerator function in terms of x divided by some denominator function. So it's basically like the ratio between two different functions. And so a lot of the times you'll have to factor to set this up. Since we're going to be, for the purposes of this video, plotting the function, I am just going to give the simplified form so we can quickly identify any asymptotes and the end behaviors of the function as necessary. So let's just get started. Our example here, we are going to be given some rational function q of x. And like I said, I'm writing this out in factored form, but a lot of the times you'll have to do this factoring step yourself. All right, so what do we know about rational functions? Well, so for the numerator function, let's check when it equals 0, right? So we basically have, and I'm going to label these two. So I'm going to say that this is nx and this is d of x. Well, so n of x, the numerator here, that whole thing can only equal 0 if one of these differences cancels out, right? So like if x equals positive 1 here, that makes this whole thing go to 0. Same if x equals negative 2, also makes this whole numerator go to 0. Similarly, if x equals positive 4. So I'm going to write that q of x equals 0 when the numerator is 0, right? And that happens when x is equal to negative 2, positive 1, and positive 4. But let's look at the numerator. There's also a way that these things can be undefined. So if dx equals 0, we get some, that's what tells us where the asymptotes are. So that's going to indicate our asymptotes. And we'll use that information in a second. But let's just figure out, okay, what happens for d of x equals 0. That tells us that, well, none of these individual factors can equal 0, so we can't have negative 3, positive 2, or positive 4. I'm just going to write x cannot equal negative 3, 2, or 4. These are undefined regions of the graph along the x-axis. Notice how there's a root at 4 right here, and there's also undefined value at that root. Think about what that means. So q of x equals 0. Let's look for the roots now. So we really just said that this is what happens. These are where the roots are, but we said that this excludes 4 because of this makes it undefined here if it is 0 in the denominator, right? So And I'm going to make a graph here. So need our x-axis. And our y-axis. That's off, we can't have that. And I want to like test different values. What I'm going to do is I'm going to pull from these and these. That's like our critical locations that are going to give us the most information. So always start out with the values that you've extracted from getting the zeros of the numerator and getting the zeros of the denominator. So we know that we have zeros at -2 and 1. So I'll just plot little points there, and then let's just see what else we have. So we have x cannot be -3. That's going to be where there's an asymptote. So vertical asymptote at x equals -3. Also 2 and 4 as well. We're going to have some problems at 2. And we'll have some problems at 4. So I'm just going to mark this. These might not necessarily be asymptotes, but I'm just marking their locations. That way I know what values to test. So here I have -3. Here I have 1 and -2. So now I'm just going to kind of look at the critical intervals, which include, and I'll just write this here, so -infinity to -3, right? Like this whole region over here, that seems pretty critical. We need to determine the behavior. So -infinity to -3 is one interval. Another one, what about, we have zeros from -2 to +1, so we're going to be interested in what's happening here, here, and then in between here as well, between the zeros and the vertical asymptotes. And so I'm going to write down the interval -2 to 1. So the interval that is bounded by both of the roots of the function q of x. What else do we have? 2 to 4, right? That is basically where I said that we're going to have some issues because they make the denominator 0. So you're going to have either a hole in the graph or a horizontal asymptote. Okay, and so with that, I think that we are pretty good. We're still going to have to find a horizontal asymptote, I think. Oh yeah, and 4 to infinity is another one. So we said 2 to 4. And then 4 to positive infinity. And what I do here is get a TI-84 calculator or just some graphing software. I'll write down the procedure for the TI-84. You're basically going to go into your y equals menu and set y1 equal to n of x, y2 equals dx, and y3 is just going to equal nx over dx, right? It's the rational function This will give you all the information that you need in one table. So I can just write in my calculator y1 over y2. And if you plot this function, it's going to give you some values, but I don't want you to plot the function. I want you to make a table. Make a table, set your independent variable to ask, independent variable to ask, dependent variable to auto, and then you can just start typing in values for x. And this is very convenient here because we're going to have to figure out what happens when we're right here, right to the left of the asymptote, right to the right of the asymptote. Same here, here, and here, and here. We're going to have to figure all of that out. What better way to do that than to just generate a list of numbers? And so I will write out by hand like one example. I just want to see what the function is doing at -4, x equals -4. So that's going to be to the left of our asymptote here. Let's just see what it's doing. So if I plug it into our function, I end up getting, so we had x minus 1, and then x plus 2, and then x minus 4, dividing through by the denominator function and substituting x plus 3, x minus 2, x minus 4. Highly tedious, but it is worth it. We end up getting 5/3, which, okay, what does that tell me? So this is like 1.667, and it's greater than 0, so it's positive, right? So it tells me we're somewhere over 1.667 is about right there. Great. Let's see what happens when we get super close, right? This is where you want the calculator, because I'll just start writing it and then you'll understand why you would want to just generate a numerical list of values, right? So this becomes pretty annoying after writing a few of the factors, and this is why the calculator is good. So calculator table. We end up getting, for these values, this is like approximately 800. And then so what I did was, okay, well, let's get even closer to -3 from the left. Right? And then I ended up getting like 8,000. This is growing from here to here. We're going up. And so, and pretty rapidly, right? So this means that as we approach this asymptote, the function is going to go straight up, right? Now, let's try to determine the end behavior. This is going to give us a horizontal asymptote, right? So I'm just going to say what happens as we go further and further out to -infinity. So x equals -infinity. Basically, what happens there, right? And so what I usually do for this, just quickly, there's a different method to do it. You'll learn it in calculus, but I'll just plug in a value like q of -20,000. Let's just see what's going on there. Turns out I end up getting 1. Let's do the other side. Let's go to positive infinity over here and see what that does. I'm expecting it to be the same. Again, not going to write it all out. This is just plugging it into the calculator. That also equals 1. Great. That means that this function, no matter how far you go out, will always approach the value of 1. So I'm just going to draw that in here right now. Horizontal asymptote. And I did that by getting the end behavior, by basically just seeing what happens as x gets very negative or as x gets very positive. Horizontal asymptote, that is a weird word. I've never heard it outside the context of mathematics. All right, and there's one thing I did not show because I did this on my calculator as well. When I plugged in Q of 4, when I said, okay, well, what's Q of positive 4? I ended up just getting 1.667. At which point I said, oh, well, that's the same as this point over here. We'll just put that there. But it actually wasn't at 4. There was a hole at 4 because it's undefined there. So there's a problem. Sorry, this is... I made a mistake again. So at Q of positive 3, I got 1.667. So I know the graph runs through that point, and then I calculated it for like right here and right here as well. So Q of positive 3.999 and Q of positive 4.001, right? So, and then I end up getting some value that is like 1.258 or something. And I got the same for both of them. And so what this means is that like the behavior isn't, we're approaching 1, right? We're approaching 1 as we go forever. We know that. And then also plugging in these bounds here, it will tell us that this shoots off into infinity, right? If we do Q of, what is that point right here, like 2.001. So right to the right of that horizontal asymptote, that shoots off to infinity. So that tells us the behavior of the graph around the asymptotes. Now, we have this whole region in the middle that we haven't dealt with yet. Basically, what we can do here is just say, all right, well, what's Q of 1? Let's just plug in. Same thing right here. What's Q of 0 is a really good one. I ended up getting 1/3 for this, and I also got 1/3 for this. And plugging in these bounds just to the right, so now Q of negative 2.999, however many you please, that is just to the right of the asymptote here, negative 2.999, and that shot off to negative large values that were negative. And then we have our defined points. And same thing here. We just evaluated Q of 1.99999, and it goes to negative infinity. Also, we know our end behavior approaches y equals positive 1 as the horizontal asymptote. And this is how you plot a rational function. And so this is a more complicated example. I'm going to do a lot more examples on this channel involving this topic because I feel like it's really important to be able to know what intervals you're working with when you're dealing with a math expression. And it actually becomes very important once you reach the topic of calculus. This will actually be a fundamental step in calculus and in differential equations, determining the domain and the range, things of that nature. So I hope this video was helpful for anybody studying algebra right now. And if you enjoyed the video, please like and subscribe it. Also, leave in the comments anything you would like me to clarify. And I would also be happy to oblige if there's anything you would like to request. So with that said, have a wonderful 4th of July weekend, and I'll see you guys in the next video.